Oh,
Okay.
gosh, yeah.
Hi. Okay. So, so we're just gonna get started. So for number one, yeah, these are really long, so we're gonna try to summarize them, or else we'll be here a long time. So, yeah, we'll try to get through this quickly. So, Elaine and Margaret studied the relationship between three linked genes affecting coat color in mice. The three recessive genes are mahogany, agouti, and ragged. The wild-type versions of these genes are dominant. These scientists carried out crosses between mice that were heterozygous for all three genes and mice that were homozygous recessive for all three genes. The following table lists the results of the test crosses, so all of those. We have our questions. So for A, determine the allele arrangement in the heterozygous parents. I guess first we can go ahead and write out what our things are. So our wild is a dominant, so we'll do the mahogany first. So wild will be our dominant. Mahogany will be our recessive. For the agouti trait, whatever, the A plus will be our dominant, and agouti will be our recessive. And then for the last trait, our wild will be our dominant RG plus, and ragged would be just regular RG. Yeah, you can see that. Okay, so what we want to do is we want to, I guess, write out the first cross that we have. So the mom is heterozygous for both. So that means we have Mg plus, A plus, Rg plus over recessive Mg, A, and Rg times dad, who is homozygous recessive straight across. So it'll be everything without the pluses. So this is our step one. Step one. Okay. Step two, basically, you just look at your chart that you're given, and it's basically just going to be the two that are most abundant. So in this case, we have one combination that gives us a total of 76 and another combination that's a total of 69. So those are the two most abundant. So those are going to be the, what are these called? Yeah, these are most likely going to be our allele arrangements. So that would be A, Rg plus, Mg, and then we have A plus, Rg, and Mg plus. So here is our answer for A. Yay, A. Okay, step three. Step three. We need to figure out, so this is where we do letter B, determine the gene order of these three linked alleles. So we have three possibilities that could happen. We have A, Rg plus, Mg, we have A plus, Rg, Mg plus, or we have Rg plus A, Mg over Rg, A plus, Mg plus, or A, Mg, Rg plus over A plus, Mg plus, regular Rg. Now what we have to do is we have to look for the two that are least abundant. So in this case, we have two combinations that both have a total of 1. So that would mean, so those genotypes would be A, RG, MG plus over A plus, where am I? RG plus and MG. So we need to find out which one of these will give us this outcome. So in order to do that, we do our little double cross squiggly thing. Yeah, that's pretty. So, and it will always go at this zigzag pattern-ish thing. So we need to figure out which one will give us this one. So we said that it should be the one that gives us A in the middle. So if we want this combination, we have A, diagonal from that we have the RG, and then we have the MG plus. So that's a match right there. And then we want this bottom one as well. We have an A plus, RG plus, and an MG as well. So this gives us a match, and we're good. And step 4, just put step 4 here. We basically just rewrite. We now rewrite the test cross with our new gene order. So RG plus A MG over RG A plus MG plus times the dad, which is recessive. Am I still on screen? Yes, I am. RG A MG. So here's our step 4. Take it away.
Okay. Thank you. So we're gonna go down to step number 5. Which we'll go right here. So for step 5, what we're gonna do is we're gonna do the cool squiggly with this. So the thing that you showed us in the video, bring it down here, up, just like that. And so that'll give us RG plus, A plus, MG plus. And it'll also give us RG, AMG. And so if we look at our table, the ones that match up with those are 16 and 18. And that'll take us to the equation where we do the 2 recessives, which are 1 and 1. And then we add in the 16 and the 18. And take that over how many there were total, which was 286. And that'll give us 17.5 when you do it in your calculator. And then that'll take us to step 6. And so for step 6, we're going to be doing this the other way. Uh-oh. So the 2 down there, and the 2 there. So that'll give us.
It looks like it's on chromosome.
It does. It looks pretty cool. RG plus, A, MG plus, and then plus MG. And so then we take those and look at the table, we're going to get 13 and 12. And then we're going to take those and put those in the equation again. So 1 plus 1 plus 13 plus 12 over 206, which will give us 13.1. Which that will take us to step 7. which is when we, a gene map.
Gene map.
A gene map. Which our gene map is RG 17.5 A 13.1 and then MG. Okay. So once we have that, we can go to step 8.
And that's our letter C answer.
Sorry, this is letter C.
50. B is the box.
There we go. So let's take us to step 8, which will be our letter D. And so for that, we're going to put these back in. So 17.5 over 100 times 13.1 over 100. So we're going to take that and we'll get our answer. So we're going to take that and put it into, we're going to multiply it by how many there are. So the 206 times the 0.0229. And that'll give us 4.72. So we're gonna put that into our last equation, which you'll see when my head moves. So 1 minus 2, or the, is it observed over expected?
That should be observed. Observed.
The observed over
Expected.
Which will give us or 57.6%. Perfect.
Yay.
Yay. So that is for question 1. For the rest of them, we're just going to kind of give you the answers now that you've seen it all written out.
Yeah. So basically, yeah, I guess should we just change the answers in the box?
I think we can just say them.
Huh?
We can just say them.
So.
Or if you want to write them out.
I don't know what I want. I don't know. I'm indecisive. So basically, we have like our new. These are now wrong, but still. First, we write out our individual dominants and recessives, all of that jazz. So then in the step 1, we write out what the mother is, which in this case is the same. All the dominants on top, all the recessive ones on the bottom, crossing with a male who is recessive all around. Yeah, and then we look at the 2 most common from the chart. You gotta scroll. Yeah, so which in this case, our answer for A should be SC plus SV over SC S plus and V plus. So this should be our answer for A. Then moving on to step 3, again, we have to write down our 3 possibilities that we can get. And we find out that the answer will be the one with the SC gene in the middle. So then so let's say that it was this one. So we would have S right here, SC plus, and then V, and on the bottom it would be S plus, SC, and V plus, and that would be our answer for B. Moving on to step 4, we would just take this cross and rewrite it and cross it with our recessive male, then that would lead us to step 5 here, or step 5. Yeah, and then again we would perform this little maneuver right here for steps 5 and 6. So for steps 5, we would add our two, the two genes, the two combinations that we use to find out which gene order we would use. So it would be 10 plus 14 plus where's my math? Plus 150 plus 156 over the total amount, which is 1,000, and then times that by 100, and our MUs would be 33 for step 5. And for step 6, again, same process. We would have, where did it go? Here. We have 10 plus 14 plus 30 plus 46 over 1,000, and then times it by 100, and we would get 10. Should be a 10, right? Yeah, it's a 10. I can't read my own handwriting. It would be a 10. So then our gene map would be, we would have our S genes, S plus S genes, and then the distance between S and SC would be the 33 MUs, and the distance between the SC and the V would be a total of 10 MUs. So that would be our answer for C. And then to determine our interference, again, we would do 33 over 100 times 10 over 100, which would give us our 0.033. And then we would add up our observed, our two least abundant, which would be 10 plus 14, which would give us a 24. And then we would use this formula again right here, which would be 1 minus 24 over the 0.033, and times that by 100, then our total percentage would be 27.3. So that would be our answer for D. Break number 3.
Okay. Awesome. So let's see here. Let's pull this up. So pardon me. So for number 3, there's an additional step. Which to understand it, we need to see that. Yeah. So to understand it, I need to explain what happens in recombination. So is that, we see that? So we can. Okay, so in recombination, you might have yeah, that's good. So you might have something like this. You have 2 chromosomes, and if the individual is heterozygous, they might have on one chromosome the 2 recessive on another chromosome. Now, what happens is when crossing over occurs during meiosis, the big A might switch places with the little a, or the little b, the big B might switch places with little b. Now, but if you have something like this, big C, little c. If you had a C that was really close to A, and what happens is when A switches over, C is very likely to switch over with A. Now, when that happens, we call that a double crossover. And let me see, why am I saying that? Yes, double crossover. Yes. Now, no, it's not called double crossover. No, double crossover. I'm sorry, hang on one second. Double crossover would be if, yes, I apologize. The double crossover would be if A and B switch over, but C does not. But since C is so close to A, C is very likely to go over with A because they're just so close. Perfect. Now that I've got that out of the way, let's go into number 3 and explain how we solved it. So, okay, so if we look at number 3, we see that there are 1, 2, 3, 4, 5, 6. There's 6 phenotype combinations. Normally we see 8, but since we only see 6, it makes us wonder, well, what's going on? Why is there only 6? Well, the answer is this is going on. Double crossover is not occurring because two of the genes are so close together they can't assort independently. It just never happens, even though we have 1,000 offspring. Not a single one of them does this because they're so close to each other. Yes, and so because of that, we are going to look for the gene combination where double crossover occurs, which is not on the list of the table. It's going to be the one that's not on there, or rather the 2 that are not on there, and the 2 are, let's see, which ones were they? I have to erase some things. I'm just erase what I drew, okay? Okay. So the 2 that are least common are going to be our G, C plus, yeah, and S plus, and, excuse me, and the G plus, C, and S. Okay, those are our 2 least common. So because of that, when we do step A, we do the same way normally. We look at the ones that are most common, which are going to be G plus, C plus, and S, and G, C plus, and S, and those are our parental offspring. They're the ones where when meiosis occurred, there was no recombination. The alleles did not move from one chromosome to the other. So it's exactly the same as it would be in the parent, the heterozygote parent. Yes, so those are going to be the ones that most likely came from the heterozygote parent because it did not perform any recombination. So now, with that in mind, let's look at So the parent is going to be G plus C S plus and G C plus S. That's going to be the gene arrangement for the heterozygote parent. Now for the gene order, so the ones that are least common, we already said, are these 2. These are the least common because they don't occur at all. So if we arrange the genes, the heterozygote, in this order, so I did step 3 to solve this one, which I won't write it out again. But what we get is we get C, S plus, and G, and yeah, C plus, S, and G plus. You see that? Yes, we can. Perfect. Okay. Okay. So this is going to be for the heterozygote parent, or in any parent for that matter. So then for part C, so the linkage map. So we did the steps we did before for steps 5, 6, and 7, and the answer when we were finished was that one second. So for this one, it's going to be C 5.6 mu, and then going to be S, and then I run out of room here. Bring it down here, and G. Okay. So this is going to be the gene map Yeah. So that's how they would appear if you saw them on the chromosome. Which of course they don't have to be in this order. It could be G in this order and C's right here, and then these would be flipped. But we don't know what order they're in, but they're in this pattern. Yeah. We don't know which one's first, which one's last, but one of these is first, one of these is last. That's all we know. Okay, now for part D. So yeah, for part D, we have to do steps. We have to go to step 8, which I already did for that one. I won't write it out again on the board. But the answer to step 8, to question part D of question 3, is 100%, because as I drew earlier, though, the A and C's were really close together, which in this case would be our C and S. They're really close together. They only have 5.6 MUs apart from each other. So they will never will assort independently, which means there's 100% interference. You'll never have a double crossover, at least not in 1,000 individuals anyway. And so yeah, that's question 3. I don't know. All right, yeah.
We have wild type, B and F, which is 379 individuals. And then we have A, wild type, which is 385. So those were the most that occurred, would be these ones. And so for B, the answer is, when we do the assortment, we have B, F, wild type, with wild type, A. So the important thing is that the F and wild type are in the middle, which takes us to C, which is B/wild type, 5.1, F, 19, A/wild type. And so here what we can see is really important. The most important thing is that the F is in the middle. The other two can be flipped. And so that'll bring us to D, which is 48.4%, which we found this by doing the same equation, but with using 19 and 5.1 instead of 17.5 and 13.1. That'll take us to number 5.
Okay. Something I forgot to mention when I was doing number 3. So when we do steps 5 and 6, so the ones here, they represent the number of times that the double crossover occurred. But because in number 3, double crossover does not occur, we instead have 0 and 0 here and here. So yeah, just want to make sure we're clear on that. Let's move on to number 5. So, okay. So the scenario is you have two genes. So maybe some room here. Yeah, no,
You're good.
Okay. Okay. So for this one, we have the same thing I had before. We had 2 chromosomes. we have an A and a B. And this one, again, is this one is little a, little b. So one of the parents is heterozygous. So, excuse me. So suppose a cell has the genotype that. Yeah. So like this. This is all in one cell. Assuming that, so big A and little a alleles are on separate homologous chromosomes. Then, okay. So for this one, we do not have this. What we have for part A is this. We have 4 chromosomes. We have B's, I don't know, it's over here. Another one over here. Yeah, so they are on 4 different chromosomes. So they can assort completely independently of each other. They don't control how they assort. So, what are the genotypes of the gametes produced by the cell? What is the frequency of each of these gametes? So what you're going to have is when the cell splits, one of the B's and one of the A's is going to go to the cell during meiosis. And then there'll be 4 cells, of course. So 2 of them, that's not 2 of them. One of them will get big A, big B. Another one will get big A, little b. Another one will get little a with big B. And then one will get little a, little b. Because they assort independently. And there's a 25% chance that this will occur. The same thing for the other 4. They're all 25% chance. They're all equal because they assort independently because they're on different chromosomes. Now for part B, suppose a cell has that genotype, so the same genotype, but in this case, A is linked to B. Yeah. So in this case, it was the thing I drew earlier. Let's do it again. So it was this one. This here. What that here? Okay. So in this case, A and B do not assort independently. If A goes over, B might go over with it. Or it's possible that A could go over and B doesn't go with it, but it's not completely independent anymore. One could affect the other now. So this problem is assuming that crossing over does not occur. Okay, so in this case, crossing over does not occur at all. If A goes over, B will go over with it, always. So in that case, instead of B being down here, it will probably be up here, right up next to A, like that. So when A goes over, it pulls B with it. Yeah. So what are the genotypes of the gametes produced by the cell? What are the frequency of each of these gametes? So you can only have big A and big B and little a and little b. They don't sort independently, so it's going to be 50-50. Okay, so that's the answer to part C. Suppose a cell has the genotype, again, big A, little a, big B, little b. Same thing we've been working with. Again, A is linked to B, and A is linked to B, just like before. And what are the genotypes of the gametes produced? I'm sorry, I'm talking too fast. What are the genotypes of the gametes produced by the cell if crossing over between these alleles does occur? So in that case, you'd have a bigger gap. So maybe B could be down here, perhaps. So that way A can go over and B doesn't go over, or sometimes they can both go over. It depends. So in that case, the gamete set will be produced the same as before. Big A, big B, big A, little b, little a, big B, and little a, little b. And then part D, this question refers to the situation in part C. So it's the same scenario. Suppose that the map distance between A and B is 7.8 mu. What is the frequency of each of the gametes produced by this cell described in part C? So this one is where it gets a little tricky. So I'm borrowing Stephanie's calculator. I think I lost mine. So in this one, what we have to do is, actually don't need a calculator for this one. I'm sorry. So it's 7.8. So now, according to the video that Sister Maya made for us, 7.8 mu also correlates to 7.8% chance of crossing over independently. So because of that, only about 8% of the time, wait, what was it? Hang on one second. Yeah, only 8% of the time, about, B will cross over independently of A. So most of the time, over 90% of the time, A and B are both going to go over. So they're pretty close, but not as close as they were before. They might be like right there. Yeah. So far enough apart that they can cross over, but they won't. I'm sorry. Far enough apart so they can cross over independently, but still so close they won't cross over independently most of the time. So in that case, to calculate the percentage for each, I still do need a calculator now. So first, let's go with big B, little b first, because it's going to be them. So what we do is we take, let me write it out, 100% and subtract from it 7.8%. And that's going to equal, it's going to be 92.2. So 92.2. So in other words, there's a 92.2 chance that that these two will not cross independently of each other, and this will be the same for these. And when that happens, half of them will be like half of the gametes, I should say, will be like this, and half will be like this, because this is a heterozygous parent. So we take 92.2 and divide it by 2 and get 46.1. So there's a 46.1 chance, or percent chance, that the gamete will have this genotype, and a 1% chance it will have this genotype. Now as for the other combination, the big A little b and little a big B, for that to occur, the A would have to cross over independently of the B. So it have to cross over and leave B behind, or the other way around. B would have to cross over and leave A behind. That only happens 7.8% of the time. So when that does happen, half the gametes will be like this and half will be like this. So we take 7.8 and divide it by 2, and it's 3.9. So there's a 3.9% chance that it'll have a gamete like this one, and a 3.9% chance it'll have a gamete like this one. And that's it. Yeah. Do you want to see anything else? Or good? Okay. Great. Thanks everybody. Enjoy your